Hello everyone. In this class, we'll look into another aspect, that's the unsteady state energy balance. For this, I will take the example of solvent heating tank systems. So here, there is no reaction involved while doing the analysis. So it is only heating a system from a base. We are just adding the liquid, hot liquid, and the temperature changes. How the dynamics of temperature change will analyze through a problem. Let's see it. So here is the problem. In this problem, we have a solvent system which is confined in a vessel, a stirred tank. So electric heating coil is immersed within it. Initially, before the heater is switched on, the solvent is present at 15 degrees Celsius and its heat capacity, that specific heat capacity, is 2.1 kilojoule per kg degree Celsius. Now also that liquid is continuously fed at a flow rate of 15 gram per hour. The heated solvent is continuously coming in at a flow rate of 15 gram per hour, and the inlet concentration is 15 degrees Celsius. Initially here also it is 15 degrees Celsius. You have 100, I think is in the next one. The tank is filled initially with a 125 gram of cold solvent at 10 degrees Celsius. So initially the temperature here is 10 degrees Celsius. It overflows. The liquid, once it gets heated, it overflows at the same flow rate, that is 15 gram per hour. So the the temperature exit is T naught, and it will remain same as the temperature in the container. It will be the same temperature. To heat this, a heating coil is given and it delivers heat at the rate of 800 watt. So what are we supposed to do? We have to calculate the time required for the temperature of the solvent here. Initially which was 10 degree, then we started adding at 15 degree from 0th time. Also along with that we are heating the solvent. So overall at the particular time the temperature of the solvent will reach 60 degrees Celsius. What is that time? We have to find out. Let's go ahead and solve this using a dynamic solution, right? Dynamic equation in the sense some rate, some quantity changes with respect to time. Here it is temperature. So basis, we'll take it as 125 gram of the solvent which is inside the tank. Let's take F as the mass flow rate as defined here, or M. Here it is M. Okay, yeah, F I have taken, written it as M here. You can take it as F in, F out. Then you have the solvent inlet and outlet streams. Tank is well mixed, so the temperature of the solvent inside the tank and exit both will be equal. Let us take something called as reference temperature, and that is usually we take it as 273 Kelvin or 0 degrees Celsius. This is for our calculation purpose. It will not have any impact on our solution, because some equation that we are using requires delta, difference in temperature. So we need we have the higher temperature, but lower temperature usually will not be there. So we do make an assumption reference temperature. So that reference temperature usually we take it as 273 Kelvin. As I told in thermodynamics concept, we don't calculate the absolute enthalpy or absolute internal energy. We calculate the changes in it, right? When I say change, starting from up to, there is a difference, right? Delta we have to calculate. So we require a temperature there coming into picture, change in temperature. So one value to other value. So at a lower most value, we'll take 0 degree Celsius reference temperature. With respect to the reference temperature, we do all the calculation. Now the flow rate is 15 gram per hour. Let's convert it to per second. That is dividing 15 by 3600. So that ends up as this value in gram per second. M be the initial value of solvent, quantity of solvent at T is equal to 0, and let me call it as M, 125 gram. And the temperature of that particular solvent which is flowing in, Ti, is 15 degrees Celsius. Let me convert it to Kelvin, 288 Kelvin. That will remain constant, that will not change. Whereas the temperature of the solvent inside the tank before the heating is started, it is 283 Kelvin, that is 10 degrees Celsius, right? 10 degrees Celsius, 283 Kelvin before the heating is started. After the heating is started, it will increase, and it's a variable with respect to time. So with respect to time, the T varies. So let me take it as a variable T. and the same temperature will be the temperature of exit liquid. With respect to time, that also changes. The heat supplied, let me take it as Q, 800 watt, that is joule per second. Specific heat is uh, since the value of quantity is in gram, let me write it in gram per Kelvin itself. So it is joule per gram per Kelvin is 2.1, right? So the total mass balance, let me write it as rate of mass in. Yeah, you may wonder why mass balance. Here we are talking about energy balance. Usually we analyze first mass balance. Once we are analyzing and completely it is balanced, then we go for the energy balance. That's the usual strategy. So let's look at the mass balance. The mass balance says rate of mass in, the quantity that comes in, the quantity that goes out is equal to quantity that is accumulated in the tank. Alright, so in this case the inlet concentration is F and outlet concentration is F. It goes out with the equal rate, so obviously there is no accumulation. So in other words, mass balance point of view, it is a steady state process. In terms of material balance, the M is constant, or otherwise it's a steady state process with respect to material balance, right? Energy balance, it is not steady state, it is unsteady state, because the temperature changes with respect to time. So that clear difference you should be able to appreciate. So let's do the energy balance now. Now energy balance, rate of energy associated with the fluid flowing in, same way as mass balance we do it, except for that it is energy, right? The rate of energy in, because it comes with the fluid, rate of energy that goes out with the fluid, right? The difference between that, and we are having a heat being supplied to the system through the heating coil, so that gets added up. So in this particular terminal, three terms here, anything that is added to the system is plus, anything that goes out of the system is minus, right? So energy as flowing in, so energy coming in with the liquid is plus, energy going out with the flowing out liquid is minus. Here the heat is supplied by the coil to the liquid, so it is plus, right? Any difference, any changes in this will be the accumulated energy in the system. So let's write in terms of terminologies. Let me clarify one concept over here. The energy, in other words, we write it as enthalpy usually. So enthalpy we write it as mcp delta T. So M is replaced with F here because it's the mass flow rate. It is F is the mass flow rate here. So it is FCP delta T. When we write delta T, we know the inlet temperature, but we need the delta T. For this reason, we take the reference temperature, which we have assumed it as 273 Kelvin. So with respect to 273 Kelvin, we are measuring the enthalpy of incoming liquid. Similarly, we do for the exit liquid, FCP delta T. So if you observe it carefully, it is MCP delta T. If at all we had taken, it would have been joule. Since it is F, that is mass flow rate, correct? So mass flow rate means with respect to time, mass per time. It will end up as joule per second. Watt is the unit over here. You have to maintain the same unit throughout. Now here it is FCP delta T, here it is FCP delta T, joule per second, and heat is being given to the system at a rate of Q, which is also joule per second. Then the accumulation term, as I had mentioned to you in the mass balance, it is d by dt of, okay, it is d by dt of. Now d by dt takes care of the time in the denominator, so the numerator must be energy. If you look at here, it is joule per second, right? So numerator is energy, denominator is time. Here also you should have the numerator energy, denominator as time. So the numerator should be energy now. What should be the energy? It should be mcp delta T, not F, because we are talking about inside the container. Inside the container, mass M is the one which you have to consider, not F. F is only for the inlet and outlet fluid. M is the inside the container, right? Same thing holds good in the material balance concept also. So there we have taken M, or volume we have taken rho Cp, right? Those things we have taken, concentration and densities we have taken in the case of material balance. Whereas in the case of energy balance, we take mcp delta T. Again delta T we take reference temperature for delta T value T minus T ref. And this T is a variable, right? So here also I have taken T, which is a variable, but Ti it comes in as a constant value. Now simplifying the whole thing, Tref and Tref gets cancelled out here. I can write it as FCP because F is constant, same way, and Cp is also constant. I can combine these two things. It becomes Ti minus T. then this q term, then here the Tref, T minus Tref, so I can write it as MCPT minus MCP Tref, right? So this can be written as two equations, two parts, MCPT minus MCP Tref. So here it is MCP dt by dt, because MCP is a constant, we have seen earlier, M is a constant, CP is a constant, you can take it out, and Tref is a constant, 273 Kelvin, right? So that goes 0, this term can be 0, so you end up with FCP Ti minus T plus Q is equal to MCP dt by dt. Now this is the differential form of your equation, right? In other words, if you want to simplify that, what you can do is dt by dt, you can take it one side, MCP take on the other side, f by m T1 minus T minus plus Q by MCP, right? This is your differential form of model equation for this heating system. Now we have to simplify this equation. So simplification in the sense, temperature term, it has to go on one side, time on one side you have to take it, correct? Before that we have substitute. So upon substitution for F, M, T1, Q, M and CP, all these values are substituted. Take care that all have the similar unit. In this case, for the mass it is taken gram, then time it is taken second, energy it is taken joule, right? Temperature is taken Kelvin. So ensure that you have taken a proper unit and it is uniform throughout. Then once you have substituted and simplified, I'm not going to show you the complete solution over here, because as you can do it yourself, it's an algebraic analysis. So upon simplification you end up with the dt by t is equal to minus 3.3 in 10 power minus 5 t plus 3.0572, right? So now this you have to integrate. When you integrate, what you have to do, you have to integrate between 0 to t. The time is varying between 0 to t. At the same time, the temperature is at 283 Kelvin in the tank, right? In the tank it is 283 Kelvin at 0th time, and the temperature for t, it is a t, it's a variable as it is. So let us take t as a function of t, right? So it will, let us not take any number over here either for this one. Upon simplification, that is, you have to integrate this equation. Now that integration, as I had mentioned to you earlier, so you will have this kind of solution, right? So minus that is, you have 1 by a plus bx. In that format, if you have, it is 1 by b ln of a plus bx. Similar to that, you have the solution here, right? The b term you have to take it first, that is minus 3.34 in 10 power minus 5, right? So ln of those two terms with the limit t to 273, 283 or 273, I guess it is 283, yeah, 283 to t, right? So that solution you have to consider, right? Yeah, you can calculate the time based on that. Time is t minus 0, because initial time is 0, final time is t. Upon substitution, you end up with t is equal to 16.73 second. So that means in 16.7 seconds, you do not take the second decimal over here. 16.7 seconds, the temperature of the solvent is reaching 60 degrees Celsius from 10 degrees Celsius, right, in the given condition. So this is the solution for that variable. The time, I mean temperature varies from 10 degrees to 60 degrees, the time required. Remember, it is not the steady state solution. If at all you need a steady state solution, what you are supposed to do? You are supposed to make that derivative 0. dt by t is 0. If at all you want to do the steady state analysis, make this dt by t term 0, right, under steady state, and simplify this. So you have only t variable here. Solve this, and that will be the steady state temperature. Now here I give you one more problem, so you can make a note of this. The solution is also available in the class notes. You can go through it in a similar way. Here the question is, in addition to the concept what we have there, here it is not a flow in and flow out, it's a fixed volume, right? So you have a fixed volume, it is getting heated up. So that you need to evaluate up to, it's given that it's boiling, so it's understood that it's going up to 100 degrees Celsius. So that's the key point here. Have a look into the numerical, check it out. Okay, yeah, thank you. That's the end of this lecture.